Good evening, sir. My name is Inskel K. Maturan from BCSE3P. Runoff characteristic of stream. Stream. A stream is a body of water with a current confined within a bed or stream bank. Streams serve as in the water cycle instrument in groundwater recharge and corridors for fish and wildlife migration. Streams are responsible for three of most important functions in the formation of landscape: erosion, transportation, and deposition of sediments. These functions are controlled by energy of the stream, and the energy of the stream is determined by the stream gradient and discharge. Types of streams: perennial stream. These streams always have a flow during dry weather. The flow of perennial stream is base flow, consisting of interflow and groundwater flow intercept by the stream. Streams that feed from groundwater reservoir are called influent stream. Perennial stream and influent stream are typical of humid region. Ephemeral stream. These streams have flow only in direct response to effective precipitation. Ephemeral do not intercept groundwater flow and therefore have no base flow. Streams that feed water into groundwater are called influent stream. Ephemeral and influent are typical of arid and semi-arid region. Intermittent stream. These streams have mixed characteristics, behaving as perennial and at certain times of the year and ephemeral at other times, depending on seasonal condition. These streams may feed to from groundwater. The following are the factors affecting flow characteristics of stream. Tulo sa kabuok gitawag og rainfall characteristic, catchment characteristic ug climate factor. Mga characteristics sa rainfall kay magnitude, intensity, distribution of time and space, its variability. Diya sa catchment characteristic, diyang soil type, vegetation, slope, geology, shape and drainage density. Diya sa climate factor, kuan, location. Runoff volume. Yeah, yields. The total quantity of the surface of water can be expected in a given period on the stream at outlet of its catchment is known as yield of the catchment in that period. The term yield is used mostly by the irrigation engineering professional in India. The annual yield from a catchment in the end of the product of various processes such as precipitation, infiltration, and evapotranspiration operating on the catchment. A common practice is to assign probabilities of various events and to assign dependability values, says 75% dependable yield. Thus, 75% dependable annual yield is the value that can be expressed to be equal to or exceed 75% times on an average 15 times in a span of 20 years. Similarly, 50% dependable yield is the annual yield value that is likely to be equaled or exceed 50 of times. For example, an average 10 times in 20 years. It should be remembered that the yield of stream is always related to the natural flow in the river. The yield of catchment, manijang kuan, formula Rn plus Vr equals Ro plus Eb plus Es. At pasabot sa Rn, natural flow in time, manag Vr volume of return flow from irrigation, domestic water supply and industrial use. Manag RO observe runoff volume at the terminal gathering station of the basin in time. Manag EB abstraction in time kaning T for irrigation, water supply and industrial use and exclusive of evaporation losses in surface water bodies on the stream. Last, kaning AS, change in the storage volume of water storage bodies on the stream. The calculation of natural natural runoff volume is of fundamental importance in all surface water resources development studies. The most desirable basis for assessing the yield characteristic of a catchment is to analyze the actual flow record of the stream draining the catchment. However, in general, observed discharge data of sufficient length is unlikely to be available for many catchment. As such, other alternate methods such as empirical equation and water wash simulation. Rainfall runoff correlation. The relationship between rainfall in a period and the corresponding runoff is quite complex and, and is influenced by a host of factors relating to the catchment and climate. Further, there is problem of paucity of data which force one to adopt simple correlation for adequate estimation of runoff. One of the most common methods is to correlate seasonal or annual measure runoff value with corresponding rainfall P value. A commonly adopted method is to fit a linear regression line between R and P and to accept the result if the correlation coefficient is near unity. The equation of the straight line regression between runoff R and rainfall P is R equals to AP plus B, and the values of the coefficient E and B are given by A equals to N summation of PR minus summation of P times summation of R over N summation of P exponent of 2 minus summation of P to the power of 2 manag B summation of R minus A summation of P over N, in which N number of observation sets are R and P. The coefficient of correlation can be calculated as R equals to N summation PR minus summation of P summation of R over N summation of P to the power of 2 minus summation of P over 2 man N summation of R to the power of 2 minus exponent of R to the power of 2. The value of R lies between 0 and 1 as R can have only positive correlation with P. The value of 0.6 indicates good correlation. Further, it should be noted. Empirical equation. Different way of estimating runoff through empirical equation. 1. The relationship between precipitation and runoff is a complicated and non-linear relationship which is dependent on several factors. 2. Forecasting and determination of the quantitative amount of created and transported runoff to the outflow point of watershed become very important. 3. The estimation of runoff volume from catchment based on rainfall runoff analysis is a very important task in engineering hydrology and can be completed using some empirical methods. Some of the empirical methods are described below. Study area. Yelahanka in Bangalore North is more or less a level plateau in the state of Karnataka, India, and geographically lies between naawa naman ninyo. Indian Irrigation Department. Indian Irrigation Department used the equation between rainfall and runoff. R equals to P 1.7 0.86, where P is rainfall in centimeter, manag R runoff in centimeter. That's okay. Kosla's formula. Kosla 1960s analyzed the rainfall, runoff, and temperature data for various catchments in India and USA to arrive at an empirical relationship between runoff and rainfall. The time period is taken as a month. His relationship for monthly runoff is formula sa Kosla formula. Managar manang monthly runoff in millimeter. P monthly rainfall in manag L monthly losses so manag T means monthly temperature. English and D'Souza formula. As a result of careful stream in 53 sites in western India, English and D'Souza 1929 involved two regional formula between annual runoff in centimeter and annual rainfall in centimeter as follows. Management formula for highland Ghat region of Western India, R is equal to 0.5 P minus 30.5. P is annual precipitation in centimeter and R is annual runoff in centimeter. SCSN method, Soil Conservation Service Code Number. Common technique to calculate the water runoff, estimate the direct runoff from a watershed by water balance equation. Maniag water balance equation. May ma-zoom ba? Mane. P is equal to Q plus F plus LA. Q over P minus LA equals Fs. Tsaka P manay total precipitation. Q actual runoff. F cumulative infiltration. Tsaka I IA initial abstraction, which represent all losses before the runoff begins. Tsaka mag-substitute ang equation. Tsaka Q ang actual runoff, formulas actual runoff maune Q equals P minus 0.2 S R2 over P plus 0.S mana P sa P is precipitation, X is maximum potential storage that a watershed can hold. Ag S maune S equals to 1,000 over Cn minus 10 is different for different soil type and condition. Ja, man yang kung problem. Calculate the annual runoff water listener by the Canton if annual precipitation is 700. Katong ganiha ang cos formula kung kaning P minus 17.8 man P. Jag answer is 14.4. 90% accurate, 20% runoff. Yeah. Para to.
Flow duration curve. A flow duration curve of a stream is a plot of discharge against the present time the flow was equaled or exceeded, as also known as discharge frequency curve. Stream flow data is arranged in descending order of discharge using class interval if the number of individual values is very large. The data used can be daily, weekly, 10-daily, or monthly values. Formula: percentage probability equals m over n plus 1 times 100%. Arithmetic scale paper or semi-log or log-log paper is used to depending upon the range of data and use of the plot. The flow duration curve represents cumulative frequency distribution and can be considered to represent the stream flow variation of an average year. The following characteristics of the flow duration curve are of interest. The flow duration curve depends upon the daily interval of data selected. For example, a daily stream flow data gives a steeper curve than a curve based on monthly data for the same stream. This is due to smoothing of small peaks in monthly data. The presence of reservoir in a stream considerable modify the virgin flow duration curve depending on the nature of flow regulation. This is the data of regulation effect. The natural flow is 100 to 50 meter cube per second and the natural flow is 25 to 78 meter cube per second. The virgin flow duration curve, when plotted on a log probability paper, plots or a straight line at least over a central region. From this property, various coefficients expressing the variable of flow in a stream can be developed for the description of comparison of different streams. The chronological sequence of occurrence of the flow is masked in the flow duration curve. A discharge of, say, 1000 meter cube per second in a stream will have a same percentage P whether it has occurred in January or June. This aspect, a serious handicap, must be kept in mind while interpreting a flow duration curve. The flow duration curve plotted on log-log paper is used in comparing the flow characteristics of different streams. A steep slope of the curve indicates a stream with a highly variable discharge. On the other hand, a flat slope indicates a slow response of the catchment to the rainfall and also indicates small variability. At the lower end of the curve, a flat portion indicates considerable base flow. A flat curve on the upper portion is typical of river basins having large floodplains and also river having large snowfall during a wet season. This is the data of flow duration curve. Flow duration curve find considerable use in water resources planning and development activities. Some of important uses are: number 1, in evaluating various dependable flows in the planning of water resources engineering projects. 2, evaluating the characteristics of the hydropower potential of a river. 3, designing the drainage system. 4, in flood control studies. 5, computing the sediment load and dissolved solids load of the stream. And last part is comparing the adjacent catchment with a view to extend a stream flow data.
Flow mass curve. The flow mass curve is a plot of the cumulative discharge volume against time plotted in chronological order. The ordinate of the mass curve is V at any time T is those Maunian formula. Then, where T is sub-zero is the time at the beginning of the curve and Q is the discharge rate. Since the hydrograph is a plot of Q versus T, it is easy to say that the flow mass curve is an integral curve or submission curve of the hydrograph. So the slope of the mass curve is dV over dt is equal to Q, while Q is the rate of flow. Mano siya ang figure sa flow mass curve. Note that the abscissa is chronological time in months in this figure. Pwede ni siya og kanang weeks, days, or months depending on the data being analyzed. The ordinate is in unit of volume in million m cube. Other units employed of ordinate include m cube per seconds day. Kani kay accumulative flow volume in mm cube. So calculation of storage volume. Assume that the reservoir is full at the beginning of a dry period. Example, when the inflow rate is less than the withdrawal or demand rate, the maximum amount of water drawn from the storage is the cumulative difference between the supply and demand volumes from the beginning of the dry season. The storage required S, so mano yung formula sa calculation of storage volume. S is equal to maximum of submission V sub D minus V sub S. V sub D is the demand volume and V sub S is the supply volume. So the storage S in the maximum cumulative deficiency in any dry season, it is obtained as the maximum difference in the ordinate between mass curves of supply and demand. So, balik ta dire. Consider the line CD of slope QD. Ano yung ijang line CD, kani CD, din ang ijang sa rate of flow, din ang tawag ang slope. Ano ijang slope QD. Q sub D. Mano siya ang demand line, kaning C to D, mano siyang demand line. Then ang ijang supply line, mano siya, kani. Mano siyang supply line. Then mano siyang storage. Then maro dire. Another example. The following table gives the mean monthly flows in a river during 1981. Calculate the minimum storage required to maintain a demand rate of 40 m3 per second. So, natay month, ng month January to December. Ang mean flow na ay 60 sa January, 45 sa February, 35 sa March, 25 sa April, and so on and so forth. Ang solution, from the given data, the monthly flow volume and the accumulated volumes are calculated as in table. So the actual number of days in the month are, so sa month, muna siya, ang mean flow, muna siya, given na siya. Ang pagkuha sa monthly flow volume, muna siya, mean flow times days in the month. So, ang mean flow na to sa January, natay 60. Ang days sa January sa 1981 nga calendar, na 31 days. 60 times 31 is equal to 1,860. Then 45 times 28 days sa February, natay 1,260 nga mean flow. Sa March, natay 35 times 31 days, natay 1,085. Sa April, natay 25 times 30, natay 750 nga monthly flow volume. Ang accumulated volume sa kaning January kay ang sa accumulated volume kay plus man sa monthly flow. So January man nagsugod mo ng 1,860. 1,860 sa January plus 1,260 is equal to 3,120. So 3,120 plus 1,085 mao ni siyang 4,205. 4,205 plus 750 mao na siyang 4,955. Sa April nga accumulated volume, i-plus po diri sa monthly flow nga May, na 5,420. Ang kani siyang 10.110 di na sa point kama na da, namali na. Kaning sa example sa July, ang isang accumulated volume is 7,630 plus 2,480 mo nang nakuha tag 10,110 sa kaning month of August ang isang accumulated volume. Plus na po na to og monthly flow sa September, makakuha ta og 13,260. Plus na po na to og monthly flow sa October, makakuha ta og 16,050. And so on. So volumes are calculated in units of cubic day is equal to 8.64 times 10 to the power of 4 m cube. Ano siya? Draw a tangential line with slope of 40 m cube second. So ang formula sa slope natay slope is equal to y over x. So ato yung ikaw ng formula, y may ang gipangita, y is equal to x times slope. So sa y natay, sa y is equal to 60.8 days, kaning 60.8 days sa month ni sa June ug July. Kaya na kaning is 1 may gipangita, storage 1. Sa 1 month kay na may average month nga 30.4 days. Sa 30.4 days, duha makabuok. Manang 30.4 plus 30.4 is equal to 60.8 days. Times 40 sa slope. Makakuha tawag 2,432 cubic day. Ano dire? 2,432. Then, ang isang storage sa 40 m cube nga demand, makakuha tag storage nga 2,100 cubic day. Pangita man na to ang maximum value sa storage 1, marisa 1,100 times 8.64 times 10 to the power of 4 m cube is equal to 181.4 million m cube. Next is calculation of maintainable demand. The converse problem of determining the maximum demand rate that can be maintained by a given storage volume can also be solved by using a mass curve. So pareha ni sa flow mass curve nga kani. Mao siya ang determination of maintainable demand. Mao ni sa flow mass curve. Ang kakuha naman ni ang V sub 1 ug U sub 2 mao na siya ang wasted, represent the water wasted over the spillway. So variable demand. In practice, the demand rate varies with time to meet various end uses such as irrigation, power, and water supply needs, or etc. A mass curve of demand is prepared and superposed on the flow mass curve with proper matching of time. So mao ni siya na mass curve of demand sa A to B. Diyan na storage, then sa A to B po na mass curve of flow. Ang reservoir and if fall sila at A and B. In the analysis of problems related to reservoir, it is necessary to account for evaporation, leakage, and other losses from the reservoir. These losses can either be included in demand rates or deducted from the inflow rates. If you use the second method, the mass curve may have negative slope at the same points. Another example. For a proposed reservoir, the following data were calculated. The prior water rights required the release of natural flow or 5 m³ per second, whichever is less. Assuming an average reservoir area of 20 kilometers squared, estimate the storage required to meet these demands. Assume the runoff coefficient of the area submerged by the reservoir is equal to 0.5. So, mao ni siya ang data nga gihatagdaan. Month sa January to December o ang mean flow o ang demand o ang monthly evaporation o ang monthly rainfall. Mao ni siya. Mao ni siya ang solution. Use actual number of days in a month for calculating the monthly flow and average month of 30.4 days for prior right release. So, sa prior right release is equal to 5 times 30.4 times 8.64 times 10 to the power of 4. Nakuhatag 13.1 mm³. When Q is equal to 5.0 meter cube per seconds. So, ang evaporation volume is equal to A over 100 times 20 times 10 to the power of 6. Is equal to 0.2 mm³. Mao na siya ang evaporation volume. Then, ang rainfall volume, P over 100 times 1 minus 0.5 times 20 is equal to 0.1 P. Mao na siya ang rainfall volume. Kung magkuhan sa inflow volume, 1 times number of days in a month times 8.64 times 10 to the power of 4 m³. So, the mass curve method assumes a definite sequence of events and it is its major drawback. In practice, the runoff is subject to considerable time variation and definite sequential occurrences represents only an idealized situation. So, the mass curve analysis is thus adequate for small projects or preliminary studies of large storage projects. The later ones required sophisticated methods such as time series analysis of data for the final design. That's all.
Good day, everyone. My name is Raisa Abigail Oramentilya from BECE 3P, and I will report about the Sequent peak algorithm. The Sequent peak procedure is used to size a reservoir. 2 cycles of inflows and drafts are analyzed. The use of 2 cycles results in the identification of the minimum reservoir capacity, which, when simulated with the design inflows and drafts, will not only meet demands but will also result in a final storage which equals or exceeds the initial storage. Demonstration of optimality follows from consideration of a method which is equivalent to the Sequent peak procedure. The Sequent peak procedure by Thomas and Burden in 1963 is commonly used to determine the reservoir capacity required to meet a stipulated demand over a given record of inflows. This method utilizes a plot or tabulation of cumulative differences between inflows and drafts as a function of a specified time interval. Appended to this plot is a second cycle of identical cumulative differences. To this author's knowledge, the reasons for using 2 cycles has never been published. It is shown that the use of 2 cycles in the sequent peak procedure results in the identification of the minimum reservoir capacity, which, when simulated with the design inflow and drafts, will not only meet demands, but will also result in a final storage greater than or equal to the initial storage. Use of the Ripple method by Ripple in 1883, or the sequent peak procedure on 1 cycle only, does not guarantee this last requirement. To demonstrate that the use of 2 cycles constrain final storage, it is first shown that the 2 cycle results can be simply obtained from 1 cycle only. So we have here a definition sketch for a sequent peak algorithm. So we have here the first peak denoted as P1, and the sequent peak 2, which is denoted as P2, and sequent peak 3, which is denoted as P3. And we also have here the lowest row denoted as T1, and the second lowest row, which is denoted as T2, where N is the number of years of record. It can be number of years, number of months, or even I don't know if there are days, pero pwede man siguro pod. And it depends on the given sa problem. And we have here the time and the volume. So for the sequent peak procedure, we have here the figure. A plot of cumulative difference between historic inflows and stipulated drafts are constructed. To this plot, a second cycle of cumulative difference is appended. So we have here the second cycle and the first cycle. The initial value, denoted as SO, of the 2 cycle plot is chosen sufficiently high so that no cumulative difference is negative. On the 2 cycle plot of cumulative differences, the value of the first local maximum is labeled as P1. And each successive local maximum greater in value than the previous labeled is a sequent peak. So we have here peak number 2, which is denoted as P2, and peak number 3 denoted as P3. Next is the lowest minimum between each pair of sequent peak. So we have here between peak, local maximum P1, and between sequent peak 2 we have the lowest denoted as T1, and between peak 2 and peak 3 we have T2 here. And the required reservoir storage is denoted as K. It is the greatest difference in value between a peak and a subsequent row. So we have here the greatest difference between the peak and the subsequent row. So dapat this is lowest minimum, which is denoted as T3 pod tera. So mo na atong gamiton na formula to get for the greatest difference in value between a peak and its subsequent row. So we have here an equivalent method. So we will use this formula. K is equals to max. The max of Pj minus Tj, Pv minus Tu, and St minus So. So the same result, however, can be determined with only one cycle by the following method. In the given figure, let Tu be the cumulative difference at the lowest point on one cycle plot, and let Pu be the highest point to the left of TU. And if TU is equal to SO, then SO, PU, and TU are identical. Then let PV here be the value at the highest point on the one cycle cumulative difference plot, and let TV here be the value of the lowest point to the right of PV. And there are also chances na ang PV ug ang TV can also be identical. And finally, let ST be the value of the last point on the one cycle cumulative difference plot, and assume that ST is greater than or equal to SO. And if ST is smaller than SO, then no reservoir capacity is feasible. The required reservoir capacity K is given by this formula. We can solve for the value of K using this formula here above. So for the constraints implied by use of two cycles, we have here spill is equals to PV minus TU minus K. Thus, spill should be lesser than PV minus TU minus the quantity of PV minus TU minus ST minus SO. Or, spill should be less than ST minus SO, but spill is equals to ST minus ST to the power of K, where ST to the power of K is the final storage in the simulation with reservoir size K. So, in equating formula 3 and 4, we have here ST minus ST to the power of K should be less than ST minus SO. So, we have here ST to the power of K should be greater than SO. So for motivation for two cycles, the use of two cycles in the Sequent peak procedure may result in a reservoir capacity greater than that required to just meet demands. A rationale for this additional capacity is clear. In using the Sequent peak procedure, the initial storage is assumed to be large enough to ensure that failure does not occur independent of reservoir capacity. Use of two cycles required that the water borrowed from the initial storage is returned before the end of the design period, and this is a reasonable requirement.
Good day everyone, I'm Roger M. Gaviola from BECE 3P. Drought. Drought is a climatic anomaly characterized by deficit supply of moisture. This may result from subnormal rainfall over large regions, causing below normal natural availability of water over long periods of time. During drought, the quality of available water will be highly degraded, resulting serious environmental and health problems. So this is the following classification into three categories proposed by the National Commission on Agriculture. It's widely adopted in the country. First is the meteorological drought, second is the hydrological drought, and third is the agricultural drought. Meteorological drought. Based on the degree of dryness or rainfall deficit and the length of the dry period. Moderate siya if the seasonal deficiency is between 26% and 50%. The severe if above 50% of the normal value. If the drought occurs in an area with a probability of P is greater than equal to 0.2 and less than equal to 0.4, the area is classified as drought-prone area. If the probability of occurrence of drought at a place is greater than 0.4, such an area is called chronically drought-prone area. In India, the meteorological drought is in general related to onset, breaks, and withdrawal times of monsoon in the region. As such, the prediction of the occurrence of it in a region in the country is closely related to the forecast of a deficient monsoon season and its distribution. Hydrological drought. From a hydrologist's perspective, drought means below average values of stream flow, contents in tanks and reservoirs, groundwater, and soil moisture. So, yung components: magnitude, duration, severity, frequency of occurrence. Studies on hydrological drought, different techniques have to be adapted for study of surface water deficit and groundwater deficit. The surface water aspect of drought studies is essentially related to the stream, and the following techniques are commonly adopted: low flow duration curve, low flow frequency analysis, and stream flow modeling. Agricultural drought. Deficiency of rainfall has been the principal criteria for defining agricultural drought. However, depending whether the study is at regional level, crop level, or plant level, there have been a variety of definitions. So, aridity index is equals to potential evaporation minus actual evaporation over potential evaporation times 100. In addition to AI index, Palmer index, and moisture availability index, which are used to characterize agricultural drought. These are useful in planning and management of agricultural operations, especially in the drought-prone areas. Remote sensing techniques using imageries offer excellent possibilities for monitoring agricultural drought over large areas. Drought management involves development of both short-term and long-term strategies. Short-term strategies include early warning, monitoring, and assessment of droughts. Long-term strategies aim at providing drought mitigating measures through proper soil and water conservation, irrigation, scheduling, and cropping patterns. So, manajang list of possible measures for making drought-prone areas less vulnerable to drought-associated problems. Creation of water storages through appropriate water resource development. Development and management of groundwater potential. Development of appropriate water harvesting practices. In situ soil moisture conservation measures. Economic use of water and irrigation through practices such as drip irrigation, sprinkler irrigation, and etc. Reduction of evaporation from soil and water surfaces, development of afforestation, agroforestry, and agro-horticulture practices, development of fuel wood and fodder, sand dune stabilization. Water harvesting, a general term to include all systems that concentrate, collect, and store runoff from small catchments for later use in smaller user areas. The collected water can also be used for groundwater recharge and storage in the aquifer. Recharge enhancement. Depending upon the nature of collecting surface and type of storages, water harvesting is classified into several categories. So, mano yung classification of water harvesting techniques. Rooftop water harvesting. Productive utilization of rainwater falling on rooftops of structures. The micro catchment system within the field of rainwater harvesting. The catchment is a small area which is not put for any productive purpose. Examples: Negari microcatchments for trees, contour bands for trees, contour ridges for crops, semicircular bands for range and fodder. Macro catchment system within the field of rainwater harvesting, designed for slightly larger catchment areas wherein overland flow and real flow is collected behind a band and allowed to be stored in the soil profile through infiltration. Floodwater farming or floodwater harvesting, used for larger catchments and the flow in the drainage is harvested. Two subsystems commonly used: water harvesting using storage structures and water harvesting through spreading of water over command. Droughts in India. Even though India receives a normal annual precipitation of 100 cm, the spatial and temporal variation leads to anomalies that lead to floods and droughts. These droughts affected the agricultural production and the economy significantly and caused immense hardships and misery to a very large population. It has been estimated that nearly one-third of the area of the country is drought-prone. Most of the drought-prone areas lie in the states of Rajasthan, Karnataka, Andhra Pradesh, Maharashtra, Gujarat, and Orissa. Roughly 50% of the drought-prone area lies in Deccan Plateau. A widespread drought in the country would cover agricultural areas of the order of 100 lakh, and the consequential loss due to damaged crops could be 5,000 crores.
Surface water resources of India. Natural virgin flow in a river basin is reckoned as surface resource of a basin. In view of prior water resources development activities, such as construction of storage reservoirs in a basin assessment of natural flow is a very complex activity. In most of the basins of the country, water resources have already been developed and utilized to various extents through construction of diversion structures and storage reservoirs for purposes of irrigation, drinking water, supply, and industrial uses. These utilizations in turn produce return flows of varying extent. Return flow being defined as the non-consumptive part of any diversion returned back. Return flows to the stream from irrigation use in the basin are usually assumed to be 10% of the water diverted from the reservoir or diversion structure on the stream from irrigation. The return flows from diversions for domestic and industrial use is usually assumed as 80% of the use. The return flows to the stream from groundwater use is commonly ignored. The natural flow in a given period at a site is obtained through water budgeting of observed flow, upstream utilization and increase in storage, evaporation and other consumptive uses and return flows. The surface and groundwater components are generally treated separately. Estimation of surface water resources of the country has been attempted at various times. Significant recent attempts are A. N. Cola's estimate on 1949 based on empirical relationships of total annual flow of all river systems of the country as 1,673 cubic kilometers. CWC 1988 on the basis of statistical analysis of available data and on rainfall runoff relationships where flow data was meager or not available, estimated the total annual runoff of the river systems of India as 1881 cubic kilometers. The National Commission for Integrated Water Resources Development 1999 used the available estimates and data assessed the total surface water resources of the country as 1,952.87 cubic kilometers or say 1953 cubic kilometers. It should be noted that the average annual virgin flow at the terminal point of a river is generally taken as the surface water resources of the basin. but this resource is available with a probability of about 50%, whereas it is customary to design irrigation projects with 75% dependability and domestic water supply projects for nearly 100% dependability. Obviously, the magnitude of water at higher values of dependability, say 75% and above, will be smaller than the average value. The total catchment area of all the rivers in India is approximately 3.05 million kilometers per square meter. This can be considered to be made up of three classes of catchment. Number one is large catchments with basin area larger than 20,000 square meter. Number two is the medium catchments with area between 20,000 to 2,000 square kilometers. And the last one is the small catchments with area less than 2,000 square kilometers. According to an analysis of CWC, about 80% of average annual flow in the rivers of India is carried during monsoon months. This highlights the need for creating storages for proper utilization of surface water resources of the country. Another interesting aspect of Indian rivers is that almost all the rivers flow through more than one state, highlighting the need for interstate cooperation in the optimum development of water resources. Utilizable water resources. Utilizable water resources mean the quantum of water withdrawable from its place of natural occurrence. Withdrawal of water from a river depends on topographic conditions and availability of land for stated project. CWC in 1988 estimated the utilizable surface water resource of the country as 690.32 cubic kilometers. The National Commission for Integrated Water Resources Development has adapted this value in preparing estimates of future water demand supply scenarios up to the year 2050. Table 5.13 gives the basin-wise distribution of utilizable surface water resource of the country. Mao ni ang average flow and utilizable surface water resource of various basins. River Indus, mao ni surface water resources 73.31. Ijang utilizable surface water resources is 46 and makita ra ni nato sa kani nga table sa PDF. In the consumption of utilizable water resources as 690 cubic kilometers, it is assumed that adequate storage facility is available for balancing the monsoon flows into an average year-round availability. The minimum storage required to achieve this is estimated as 460 cubic kilometers against the present estimated total available storage capacity of 253 cubic kilometers. If more storage capacity could be developed, carryover from years of above normal rainfall to dry years would be possible. For comparison purposes, for about the same annual runoff, the USA has storage of 700 cubic kilometers. Utilizable dynamic groundwater resources. The total replenishable groundwater resources of the country has been estimated by CGWB as 431.89 cubic kilometers per year and utilizable dynamic groundwater potential as 396 cubic kilometers per year. Water available from return flows. Water used for specific gravities such as irrigation and domestic water supply includes consumptive and non-consumptive components. The non-consumptive components part of water use is returned back to hydrologic system either as surface flow or addition to groundwater system or as soil moisture. However, due to economic and technological constraints and due to possibilities of diminished water quality, only a part of the return flow is recoverable for reuse. The utilizable return flow is an important component to be considered in the demand-supply analysis.